Okay, welcome back for AC analysis. And in this example, we are going to analyze this circuit for AC. I'm not going to solve this for DC because I have tackled DC so many times, and you can solve this in DC using voltage divider method, which is well-known method, and I think it should be clear for you. So I'm just going to focus on AC analysis, and still DC analysis is quite important because from DC analysis you have to know IE, and IE here is given as two like points. If you solve it, you'll find approximately IE is equal to 2.77 milliamps, and the thermal voltage is given, it's approximately 25 or 26 millivolt. And if you notice, this circuit is common emitter. Why it's common emitter? You can see here. You can see the output. You can see clearly the output. V out. V out is connected to the. Okay, I'm sorry. Like Microsoft Word has stopped working for a moment. Anyway, okay, so you can see V out is connected to the collector, and the input signal Vs is connected to the base. So which left is the emitter. So we can say this is like common emitter. Okay, now another thing to notice, like just to notify you about, is the RE resistor. You can see here we have like RE is split. We have RE1 and RE2. Now, again, I have mentioned this in our classes so many times. The capacitor in DC analysis, it works as an open circuit. So in DC analysis, this is going to be open circuit, okay, and you have to um, consider that RE is equal to 300 ohm plus 700 ohm, which is equal to 1 kilo ohm. So in DC analysis, RE is equal to 1 kilo ohm. Now, in like AC analysis, okay, RE is equal to only, like it is only RE1, which is 300 ohm. Why? Because in AC analysis, the capacitor acts like a short circuit, and this RE2 is going to be like bypassed, so we will ignore RE2 from our calculation. So once you go for DC analysis, you have to consider RE is equal to 1 kilo ohm. Once you go to AC analysis, you have to consider RE as only equal to RE1, which is 300 ohm. Okay, I hope also this is clear for you. And another point I wanted to mention regarding beta. Okay, now generally speaking, like the DC load line in DC is not exactly the same that the AC load line. In AC load line, we have a small shift, and this is because of beta. Beta AC is a little bit greater than beta DC. For example, if beta DC is equal to 150, beta AC it could be 175. However, generally they are close from each other. So most likely if you see beta, like one beta, that means here we consider that beta AC is equal to beta DC and it is equal to 150. But if you see, for example, beta DC, let's say, is equal to 150, beta AC is equal to 175. Also here you have to be careful. For DC analysis, you have to consider this. This is for DC, and for AC analysis, you have to consider this. Okay, so this is just to be careful. But however, in this numerical problem, beta is equal to 150. We have only one beta, so for DC analysis, you substitute beta as equal to 150, and for AC analysis, you substitute beta as 150 as well. Now, common emitter circuit is known as high voltage gain and a current gain. There is also a current gain, and usually high input impedance and like normal or medium output impedance. So high input impedance and medium output impedance. Okay, and it has a voltage gain, high voltage gain, and it has a current gain. So like if you are looking for voltage gain and the current gain, so this configuration is quite helpful. Okay, so let me start this analysis. And as you see here, now from DC analysis, you need IE because we need to find RE, which is the dynamic RE resistance. Okay, let's see now. First of all, we have to find ZO. What is ZO? ZO, it is the output impedance. Okay, it is the output impedance. And I told you, sorry, forgive me for this, but my mouse is broken and it's keep messing around. So like it will do this kind of stupid things over and over. Anyway, so you can see what is ZO. It is the output impedance. It is the output impedance here. Let me choose the green one. Okay. And well, before tackling these like parameters, let me plot this circuit, okay, in like the AC equivalent circuit, and let me also plot the BJT transistor in AC mode using hybrid pi model, and we will see how it's going to look. Okay, so so this is the VS, which is the AC source, VS, and this is RS, and this is the capacitor, which is going to act like a short circuit. And you know here, VC is going to be killed, right? This is how to draw the AC equivalent circuit. So it's going to be grounded. So R1 and R2, they will become grounded and they will become in parallel. So here we have R1 and R2. Okay, and then we have our transistor here, and this is R pi. Okay, and this is R E1 only, and this is grounded, and here we have beta IB, and finally here we have the output. the output impedance, which is RC, and RL, and this is the output. Of course, I have ignored RO from our calculation. Now here, of course, R pi is equal to what? Is R pi is equal to beta R e. So this is equal to beta R e. Now, so what is output impedance? What is the output impedance? So output impedance here, ZO. You will see in order to find the output impedance, you have to kill the sources. So this is going to be like how to kill a current source is going to be open circuit. So open circuit, that means this part is like has been split from this part, and you have to short circuit this. So this is going to be a wire, and you can see now what left for ZO is RL and RC, and you can see that RL and RC, they are sharing two nodes, this node and this node. So we can say that ZO is equal to RC in parallel with RL. So it is 10 kilo ohm and it is 8 kilo ohm. You can use this website if you like. Okay, so it is 10 kilo ohm and it is 8 kilo ohm. Okay, I want my answer to be in kilo ohm, so it is approximately 4.45. So I'm going to say here ZO is approximately 4.45 kilo ohm. Okay, so that's ZO, and this is done. Now for AV, which is the internal voltage gain for the transistor. Okay, now, okay, okay, I just need to extend this word. Okay, so sorry for this, guys. Okay, like, okay, okay, so okay, so I'm looking for now AV. Okay, I have derived this. I told you AV is what is equal to minus the output impedance ZO, or you can say RC in parallel with RL, which is the output impedance, by RE plus RE1. Okay, this minus means that the input signal and output signal, they are out of phase. So we have inversion by 180 degrees. But actually the gain is positive. It's not negative. This is just to tell you that the input signal and the output signal, the phase, like their phase is like they have inversion in their phase. So that's it. In common emitter, like the input signal and output signal, they are not identical. They have a phase, inversion in the phase is equal to 180 degrees. That's what the minus means. So I need to find what is RE. RE, which is like it is the AC emitter resistance, or the dynamic, we call it also the dynamic resistance for the emitter, is equal to VT by IE. So this is 26 millivolt by 2.77 milliamps, milli by milli. So RE is approximately equal to 9.386 ohm. Okay, so that's RE. So now I can go for the gain. Okay, so the gain is going to be the output impedance is 4.45, of course, kilo ohm. Okay, by um, okay, RE plus RE. So you can, like, let me use the calculator. So RE1 is given here. RE1 is 300 ohms, so it's going to be like 300 plus RE, like small RE, plus 9.386. So divided by 1000, since my input output impedance is in kilo ohm, so it is going to be like 0.309 approximately. Okay, and it is going to be like approximately 14.35. So that's the gain. That's the gain. And it's done. So it's done. Oops, the pen is messing around. So now we need the input impedance, Zin. Okay, first of all, to find Zin, find Zi. So find Zi, because once Zi is ready, Zin is easy. Zin is equal to Zi plus Rs. So finding Zi, what is Zi? Zi is this: R1 and R2 and this resistors are pi and RE1, and all of them, they are in parallel because they are sharing the upper node and the ground. So like, you need to find what is this resistor, and I have also derived this to you, and I can tell you this resistor is equal to what? This resistor here, this resistor, let me change the color. This resistor here is equal to beta RE plus RE1. Okay, so what is my beta is 150. Okay, so it is 150, and RE plus RE1, it is, so let me find this. Okay, so here's my, this is already in kilo ohm. Let me multiply it by 150. Is my beta 150? Yes, it is 150. So this is 46.4 almost. Let me go to this website. Okay, and what is R1? R1 is 28 and R2 is 6, so 28, pardon, 28 and 6, so it is approximately 4.9. Okay, so I'm going to say it's going to be like 4.9. So yep, 4.95. So I'm going to say now Zi, now Zi is equal to R1, R2 with beta RE, RE plus RE1. So you find it like just substitute, okay, and it's going to be like approximately 4.95 kilo ohm. But I don't want Zi alone. I'm looking for uh, Zn. So Zn is going to be 4.95 plus 400, right? Okay, because you can see Zi plus Rs. Rs is 400, so plus 0.4 and approximately is equal to 5.35 kilo ohm. So that's is the input impedance. Okay, so that's done. Now we are ready to find the total gain, like total voltage gain. Okay, AVS, I also have derived this to you. So let me choose this one. So AVS is equal to the internal gain for the transistor multiplied by Zi by Zn. Okay, so obviously Zi by Zn is less than 1. Okay, so this is going to be like AV. We found AV. How much it is? It is 14.35 times Zi is 4.95 by Zn 5.35 kilo ohm, and it's approximately is equal to let me it's 13.278. And of course AVS is less than AV because as I told you Zi is less than Zn, so this ratio here is must be less than 1, okay, times AV. Okay, so it is approximately, usually it is 90% of AV. It depends of course on how much RS is. Okay, so that's how to find the total gain. Okay, so this is done. AVS is done. And now the total current gain. Okay, now the total current gain, and you can do this in two ways. Okay, and I will show you both of them. Okay, so the circuit current gain. Okay, the circuit current gain. Okay, let me use this color. Okay, now we can say the current gain, total current. I'm not going to say I'm not only here asking to find like what is the current gain for the BJT, because I know what is the output, it's IC, okay, and what's the input, is IB. So it is almost beta. No, I don't want that. I'm looking for the total current gain for the circuit. So I'm going to say it is I out by I in. And this is small I because we are in AC domain. So what is I out? It is obviously a IC because what's the current? What's the output current? And since V out is connected to the collector, so it's going to be IC. So I out is IC. So I out is simply IC. So we need to find IC. IC in AC. Okay. So uh, how to find IC? Now here, if you let me back to this AC circuit. Now, once you find ZI, what does that mean? That means once you find Zi, this resistor R1 and R2 and R pi and RE1, they are all going to be in one resistor. And we call this resistor as like Zi. And here, now, here, this is Vi. Okay, so I need to figure out that's what is IC. I need to find IC. So why I'm interested in Vi? Because if I find IB, I can know what is IC is and vice versa. So I can say now VI is what? Let me apply like I times R, right? So it is equal to IB, right? But I can write IB as IE by beta plus 1. I can write like that times R pi, right? Okay, so it is this current is IB. Like here we have this current here is let me let me like oops. Okay, so this okay, so this current here is IB and this voltage from this point to this point is like VI. Okay, so VI is equal to IB times R pi. But why I wrote IB as like IE by beta plus 1? Because I need to make this resistor and this resistor in series. And in order to do so, I need to make the current is the same, right? So rather than saying it is IB, I just said it is IE by beta plus 1 times beta times R pi, okay, plus IE times RE1. Here we have the current, which is this current is simply IE because here we have the emitter, okay, and here we have the base current. So that's the trick. We want to make them in series. So rather than we say it is IB, okay, we say IE by beta plus 1 times R pi. So now VI is going to be IE by beta plus 1. What is R pi? It is beta RE plus IE times RE1. So like you can ignore this one. So beta plus 1 cancels beta. So we can say VI is equal to IE times RE plus IE times RE1. So it is like IE, we factor it out, times RE plus RE1 between parentheses. So that means I'm looking for what? I'm looking for IC. Okay, so IE, like it's almost is equal to IC, since also you can notice that I have ignored this one. So I can say now simply I'm looking for this guy IE. So IE is equal to what? VI by RE plus RE1. Okay, so let me extend this file again. Okay, now I need to find this VI, this input in P, this voltage here. Sorry, this voltage. What is this voltage? VI. I don't know VI. How to find VI? Like, let me simplify this part. Let me simplify this part. I can simplify this part like this. You can see this input part here. Like, I can simplify it like this. I can replot it, something like that. This is my Vs, and this is Rs, and this Zi, right? Zi is a combination of R1 and R2 and beta Re plus Re1. Okay, so and this is going to be my Vi, this voltage. So simply you can apply voltage divider. You can say Vi is equal to Zi by Zn, or Zi plus Rs times Vs. So you have Zi, you have Vs. Vs is given. Here you can see Vs is given. This is it's equal to 220 millivolt. So you just substitute those numbers. Okay, you substitute them. Okay, this is okay. So you substitute it. If you want this in volt, substitute this in volt as well. So it is like 0.22 volt. Okay, and this in kilo ohm and this in kilo ohm, it doesn't matter, it is a ratio. So you can find out that Vi is approximately equal to 0.203 volt. Okay, so now everything is ready. Just plug Vi there. So that means IE is equal to 0.203 by Re plus Re1. Okay, so this is like 309.36, and of course this is in ohm, and this is in volt, so your answer is going to be in amps. So whatever the answer is, just multiply by 1000 and you will get the answer in milliamps. So this is the answer, like it is approximately, of course, in milliamps. Just be careful here. The the answer is going to be in amps, but I just multiply this directly by 1000. Okay, so it is approximately 0.65 milliamps. So this IE is done. Okay, but I am not completely or I'm not 100% over it, because I know I'm looking for total current gain, and it is I out. So I out is equal to ICO, which is approximately equal to IE, okay, by IN. I need to find what is IN. Okay, let me back to this circuit. And what is IN? This is IN. So you can say, okay, now you know VI, right? So it is going to be, this is VS here, and this is VI here, okay? So no need to highlight them again. You can simply say, from this circuit, what I in, this is I in, okay, is equal to Vs minus Vi, the voltage across that resistor, by Rs. You know Vs is given, Vi, we just found it, Rs is given, just substitute those values and you will get In as In is going to be approximately 0.0425 milliamps. And again, just be careful about the units, okay? Okay, that's what I also want to emphasize about. And now, finally, now we are ready because IE is known and IN is known, okay? So also this is like known. So we can say, oops, okay, we can say, oops, sorry guys. Okay, we can say now we are ready to find the total current gain. So the total current gain, the total current gain is IE, which is 0.6561 by IN, which is 0.0425, and it is approximately going to be 15.45. And we are done. Oops. We are done. Just let me highlight the answer here. Okay. And I told you I'm going to show you two methods. This is the first method to find the total current gain. There is like a shortcut, and I'm going to show you from where this shortcut has came. So we know, we can say like this is a shortcut, okay? Like let me select this. We can say like shortcut. How? We know what is the shortcut to find current gain. Okay, we know that the current gain is what? Is the output current by the input current. So we can say the current gain, total current gain is equal to what? Is equal to the I out, okay, I out by IN. Okay, and this, what is I out? It is I, we know this, but we can also say it is V out by the output impedance by V in by the input impedance. So this is going to be V out by ZO times Z in by V in. Now, V out by V in, this is the total voltage gain times Z in by ZO. So this is going to be total voltage gain times Z in by ZO. Now, if we substitute AVS and ZN and ZO, we should get a similar answer. So AVC is what? AVC is, we got it. The total voltage gain is what? Is 13.278, and so it is 13.278 times Zn, okay, by ZO. So Zn is 5.34, almost like, or 5, I think, okay, by ZO, and ZO is approximately 4.45. So we can say, okay, 5.35 divided by 4.45 times 13.278, and it is equal to 15.95, I guess. And you can see here 96, okay, and here it is 15.45. It is almost the same answer. Like, this is like, also you can use this method or this method. Now I'm going to tell you, what if Rs is equal to 0? Suppose this Rs is going to be 0. Okay, what's going to change? Let's say, assume that now we don't have this Rs. What's going to change? Now, first of all, if Rs is equal to 0, that means AV is equal to AVS, because in this case we know AVS is equal to internal gain times Zi by Zi plus Rs. Rs is 0, so Zi by Zi is equal to 1, so AVS is equal to AV. Now that's first. Now for the current gain also, what's going to change in this case? You can see here, I'm going to tell you what's going to change. If you want to find the total current gain using the first method, you can see if Rs here is 0, you can simply now say Vi is equal to Vs, because they will become in parallel. Vs and Vi, they are going to be the same. So that means Vi is going to change, and that means IE is going to change, and for IN also it's going to change. Okay, so I just wanted to highlight this point. Okay, I hope this presentation is clear for you, and now the common collector common emitter circuit, especially in for AC analysis. It's clear for you, and that's all. Thanks for watching.